at your exams. And again, overall, good job on those. Before we get into our new material, I emphasized this at the end of the last semester that factoring is going to be important. You will not be able to do what we're about to do if you cannot factor effectively. So, before we get too far ahead of things, I want to do a little bit of factoring review. I know we looked at factoring as we were going over the exam, but I want to review some factoring with you. Go and jot this polynomial down in your spiral notebooks. You don't need your textbooks just yet. 6x squared minus 4xy cubed. And remember we said the first thing we always check for when we factor, class? Common factor. And so what's common in this polynomial? Maddie? Good, there's a 2x common. And we pull out the 2x, what are we left with in parentheses, Maddie? 3x. Great job, 3x negative 2y cubed. We just divide out the 2x, because remember factoring is division. Will there always be a common factor? Well, no. For instance, in this next polynomial I have you copy down, there's no common factor there. But it's one of our special factoring cases. Brecken, do you recognize what we have here? Very good. Difference of squares. And a difference of squares factors into, very good, the sum and difference. What's the sum and difference going to be here, Brecken?
2x minus 3y. 2x.
There we go. I normally do the plus and then the minus, but it doesn't really matter. A difference in sum is the same thing as a sum and difference. Multiplication is commutative. Yeah, 2x plus 3y, 2x minus 3y. We also might look at something like this, where no, there's not a common factor. But again, this is a special case, Noah. We've got a three-term expression with a perfect square, positive, even. We would call this a and a perfect square trinomial factors into a binomial squared. What would the binomial be? And remember, we want to check with that whole multiply and double thing. 3 times 1 would be, and if you double a 3, you get 6. So there we go. It all checks out. Now, I did say you could also do what with this trinomial? Gavin? You could treat it like a backwards FOIL scenario. And in fact, in the chapter we're going into now, we actually prefer backwards FOIL. Okay, you'll see why as we go along, but we're actually going to prefer the backwards FOIL where the x squared would factor into, well, the x squared factors into x and x. The positive, remember, tells us, and in this case, they're both going to be negatives. And the 9z squared, make sure we don't forget about the z squared. Getting some interesting looks from people who remember as they looked at the exam. Oh, I did it again. But the z squared factors into, right, z and z, and then the 9 into 3 and 3. And of course, your outer inner gives you negative 3xe, negative 3xe, negative 6xe. Notice it's the same thing as x negative 3z quantity squared, but for what we're going to be doing, you're going to benefit from having 2 separate factors as opposed to a single factor with the exponent. Of course, if we had something like this, we've got perfect square, but not positive and not even in the middle. So it's not a PST. And if it's a trinomial and it isn't a perfect square trinomial, then what do we kind of have to do anyway, Maddie? Then backwards FOIL is really our only option. So for our purposes, pretty much any trinomial, let's go to the backwards FOIL. If it's a trinomial, we're just going to backwards FOIL it. That's going to make our life easier, more simple, as opposed to looking for that binomial squared option. So, Maddie, as we factor this, what do we get? Okay, and just one little z and z, yeah. All right, so you're right, the x and x signs are going to be different based on this, so we're going to have a negative and a positive. The z and 2 and 2 would have canceled each other, so Maddie wisely put the 4 and the 1 with the 4 being the negative, so the outer inner did give her the negative 3xz. Some backwards FOILs harder, though, than others. Anytime you've got a leading coefficient other than a 1, the backwards FOIL does become a trifle more challenging. So, Brecken, as we look at this one, we see trinomial. We identify there are no common factors. We're ready to backwards FOIL. But it's not just x and x. We also have to take care of the 6. probably we need to factor it. Probably 2x, 3x. It might be 1x, 6x. I don't know. Just put it down and let's get, you sit there too long, you get yourself frustrated. Just put it down and see what happens. We then look at the last sign. Of course, it's negative, which again tells us. So we just put, and again, if they're wrong, we'll change them, right? We're going to figure it out. Just put it down for now. I don't want to forget about my z squared. That would be traumatic, wouldn't it? And so we're going to factor the z squared. Yeah, we get the easy part out of the way. And now the 4. With a 4, normally we would think, I would normally think 2 and 2. But because of the 2 here, I can't do a 2 and 2. So we're going to have to try. But can I put the 4 here where the 2 is? So if I'm going to do 4 and 1, I need to put the 4 here and the 1 here, correct? So again, just kind of keeping in mind there wasn't a common. Now, listen, if there is a common factor here, you will get a common factor in one of these, guaranteed, okay? So that's why it's important to get the common factor out first, or at least confirm there isn't a common factor. We confirmed there wasn't. That's why we could use that check. Well, let's just do outer inner and see what happens here. Brecken, outer. Well, keep the sign as well. Negative 8xz, correct? We got the negative times the positive. All right, and then with the inner, a positive 3x. Again, be sure to include the sign number letter. So negative 8xc, positive 3xc gives us? Look at that, we got it on the first try, right? Don't sweat it, just get stuff down. If it hadn't worked out, we would change numbers around or change signs around, and still didn't work. Maybe we try the 1 and 6 instead of the 2 and 3. Just stick with it and keep trying. And then there was a last factoring method that we looked at involving bigger polynomials than simply your trinomials. We said if there's 4 terms in the polynomial, Noah, we're going to factor using a method called grouping, where instead of looking at the whole thing for a common factor, we only look at them in groups of 2. In Algebra 2, we'll look at 6-term polynomials. We can group them in 2s or 3s. 9-term polynomials have to group in 3s, things like that. So grouping actually works for more than just 4 terms, as long as it can be grouped equally. Odd number terms, like 5, you can't group because 2 and 3 wouldn't match, right? But 2s, 3s, something like that. So here, just go with groups of 2. In the first group, what is common?
2x.
And we factor out the 2x it leaves us with.
3x.
There we go. What about in the next group? What's common? But remember, we're always in grouping going to use the sign of the first term that's being grouped. So since there's a negative leading here, it's not just the z, but we're going to factor out a negative z. So as we're dividing it out, remember, it's not just a z, but a negative z. You pull a negative z out of a negative 3x z, it gives you good. Positive 3x. And no, if you pull a negative z out of a positive 2yz, it gives you
Positive 2y.
Signs are different. Right, remember sign number letter, we're just dividing. So when we divide the sign, we end up with the negative. The 2 divided by 1 is 2. The y doesn't cancel with anything, but of course the z does. Now, that's important that in these 2 terms that we have remaining, that the binomials match. If they didn't match, well, we just can't factor it. Whatever, we gave it a good try. But they do match. So therefore, just as we could pull out a common monomial factor, Gavin, we could also here pull out a common I have 2 terms, 2x, 3x minus 2y, and negative z, 3x minus 2y. What's common? Class? 3x negative 2y. The entire binomial factor is common. So just like, remember, if we had like a 2, this is bad, 2mx minus mz, you say, well, there's an m in both of those. Pull it out. Well, here it's not an m, it's a 3x minus 2y that's in both of them. But just like we would pull the m out, we can pull out the 3x minus 2y. What's left, back to Gavin, we pull the the 3x minus 2y out of each of those terms? 2x negative z. Notice we end up with dissimilar binomials when you factor by grouping. It's kind of an overview of all the different factoring methods we talked about last quarter. Questions on any of these before we begin our new material? All right, that said, then in your notes, next section, rational expressions. Rational expressions. We talked about classifications of numbers back at the beginning of the year. We talked about this term rational numbers. And I said a rational number is a number that can be written as a ratio of two integers. In other words, a number that can be written as a fraction. Essentially then, in algebra, whenever you hear the word rational, it always refers to fractions, ratios. So in parentheses, after you've written the official title, rational expressions, which sounds really smart and slightly terrifying, just put fractions and stuff in parentheses. Fractions and stuff. Because that's really what rational expressions are. They're simply fractions and things pertaining to fractions. Quick refresher for you on fractions and stuff. A fraction has two parts. It has top part, then there's the fraction bar, and there's the bottom part. Now notice the way I worded it. There's a top and a bottom with a horizontal fraction bar. You're gonna get yourself in trouble in this chapter if you go with a slanted fraction bar. Don't do it. Okay, or actually from your perspective, it needs to be like this. Don't do the slanted fraction bar. Have a top, have a bottom. Even if you end up burning 2 lines on your page to do it, have a top, have a bottom. It's gonna be so key to your success. What do we call that top number, class? The numerator. If you want to, if you didn't know that or needed the refresher, go and write that in your notes. The numerator. Numerator. And the bottom value in a fraction or rational expression is called the denominator. Denominator. Okay. So the numerator and the denominator. And again, the purpose of a fraction is simply to show parts of the whole. For instance, if we said, well, how many of you had a good Christmas break? Raise your hand. All right, 2 out of 4 of you had a good Christmas break. All right, sorry, Gavin and Brecken. All right, but it shows the parts of the whole. How many of you did have a good Christmas break? 2 people raised their hands. How many total people are in the whole group? 4. So that's the purpose of a fraction, to show parts to the whole. The numerator shows how many parts satisfy the given condition, and the denominator simply tells you how many values, in a sense, are in the whole group. So parts to the whole. Now, if we look over at the side there, I've gotten a lot of comments on that poster throughout the year. It says math illiteracy affects 8 out of every 5 people. If that bothers you, then you're not one of those people. But if it doesn't bother you at all, you see absolutely nothing wrong with that poster, you're part of the problem. Math illiteracy affects 8 out of every 5 people. Because if there are 5 people, how many of them could have this problem? At most, 5. You can't have more people with a problem than you have people. Now, you could have more problems than people, right? Because somebody like Noah might have a lot of problems. But might. I didn't say he did. But I'll let you guys judge that one. But anyway, you can't have more people with a problem than you have people. This is one of the question marks about this latest election, right? Feels like we have more votes than registered voters. Something is wrong. But of course, you can't prove anything apparently, and the courts don't want to hear it, so whatever. We just look the blind eye and let the swamp take over. But I digress. Any fraction in which the numerator is greater than the denominator is called an improper fraction. An improper fraction. You say an improper election if more people vote than are able to vote, because somebody voted twice or somebody wasn't supposed to voted. You know, dogs voted and whatnot, okay? But anyway, I don't think a dog actually voted, but there was actually a ballot sent to a dog. Somehow, yeah, I don't know, it's weird. But anyway, improper fraction, where the numerator is greater than the denominator. Typically, we would expect to have a greater denominator. That should generally be the greater value, in which case we refer to it as a proper fraction. But there is one important aspect to a fraction that we must understand. If you're showing the relationship of parts to the whole, you cannot have a whole of 0, because then you have nothing to compare, correct? So it's important to write this down, that the denominator can never equal 0. The denominator can never equal 0. Now, if you're just working with numeric fractions, just don't write a 0 as the denominator, right? That's pretty easy. But what about if we were to have something like, turn to page 409, turn to page 409, and as you're turning, the first problem we're going to look at is this one, because we're working with rational expressions here in algebra, meaning you're going to have variables in your numerator and denominator. Here our denominator is x minus 3. But it's important to understand this cannot be 0. Well, I mean, if x is like 10 minus 3 class is 7. You're good. You don't get a 0 then. If x is like 5, well, 5 minus 3 is 2. That's not 0. If x is 0, what's 0 minus 3? Negative 3. It's okay, it's been a long vacation. But it was a good one, at least for him. All right, negative 3. That's not 0. But what number, class, if I tried to plug it in right here, will give me a 0 in the bottom? 3. Do we all see that if you tried to plug a 3 in here, 3 minus 3 would equal 0? So with this rational expression, x cannot equal 3. That is a restriction on this rational expression. So with algebraic fractions, when there are variables in the denominator, you have to catch what values cannot exist there. Well, let me help you out here. Just simply state, first of all, that the denominator, x minus 3, can't be 0. Does that make sense? And then, x can't be 3. And with this one, frankly, we should be able to see, yeah, 3 minus 3 would equal 0, but we'll have problems that are a little bit more challenging. So the key then would be to set the denominator unequal to 0 to determine which values of x are what we call excluded values. Does that make sense? Take a look at number 14. They give us the rational expression 7x plus 2 over 5 plus x. Without doing any math, can anyone think of the number you better not try to put in for the x? 5 plus 5 would be 10. We're good. How about the inverse? Negative 5, right? Do we see that if we tried to plug a negative 5 in here, 5 plus 8, negative 5 would have equaled 0. You're not allowed to have that. Again, what's your strategy? Set it unequal to 0, and then move the 5 over to get x cannot equal negative 5. And that shows what value is excluded from possibilities. X can be anything else, it just can't be negative 5. In the previous example, x can be anything except can't be 3. Just not that one. Does that make sense? All right, kind of like for football fans, you know, we're like, all right, football's championship coming up, my team's out of it, who do we want to win? Just not Bama, for instance. We just, anybody, or for so many years in the NFL, anybody but the Patriots. We're just sick of seeing the Patriots win. Anybody but the Patriots. You know, I'd love for my team to win, but let's be real. So anybody but the Patriots, you know. That's kind of how we're going about this. X can be whatever, but not this one thing. Or in some cases, not these two things. Look at number 15. Set that denominator unequal to 0. And then solve to determine which value is excluded for x. Pencil down when you've got it. Remember, are we locked in on the numerator or the denominator, class? denominator. By the way, you're going to hear me say this a lot throughout this chapter. I don't care about the numerator. All I care about is the denominator. Okay, that's all I ever really care about in algebra is that denominator. Numerators, whatever, I don't care about that. You know, you ever feel like a numerator, nobody cares? Well, y'all are like denominators, and I care very much about you, especially what you can't be. That's failures. All right, so what do we need to do to figure out what x cannot equal, Brecken? Make it not equal to 0. Now, once you've done that, we need to get the x by itself, right? So to get the x by itself, first let's move over the has a, and that gives me what statement? And then to finish getting the x by itself, I simply need to divide away the 2. So x can be anything in this expression except it cannot equal -1/2. Does that make sense? Did anyone get -1/2? All right, a couple of you already started to catch on to what we do here. All right, let's take a look at another one. Number 16. Figure out what it is that x cannot equal. Figure out on number 16 what it is that x cannot equal. Maddie's got it. Maddie, what you got? 5. Cannot be 5/2, right? How many got 5/2 as the excluded value on number 16? Gavin, question.
Yeah, -5.
All right, you take the 5 minus 2x. You set it unequal to 0, so bring the 5 over first to get negative. Don't lose it. 2x cannot equal. Now -5. We need to divide away the -2. Negative divided by negative, they cancel away to give you just 5/2. Does that make sense? Now look at the next one though. Because number 17, that denominator is quadratic, isn't it? It's got an x squared. So when we set this denominator unequal to 0, do you realize there will be 2 things potentially that x cannot equal? Does that make sense? What do you suppose we would do? Well, this is not a quadratic equation. It's a quadratic unequation, if you want to call it that, right? Technically, quadratic inequality is what it's called. But we're going to solve it the same way. We're still going to go ahead and factor the x squared plus 2x plus 1. How would we factor this, Gavin? Good. Check your outer inner. Do you get 2x? All right. So when we set each of these now, not equal, but rather unequal to 0, what do we get for our excluded values? X cannot be, class, -1, or x cannot be -1. We don't actually need to write that twice. We'll simply write it once. X can't be -1. So in this expression, there's your one excluded value. Questions on that? Take a look at the next one. 5 over x squared minus 9. What do we need to do to determine our excluded values, Noah? Not equal to 0. There we go. Not equal to 0. We're used to setting it equal to 0. Now we're setting it not equal to 0. And of course, then we need to. It's quadratic, right? Because of the squared. So instead of bringing the 9 over, let's factor it instead. Factor it into. There we go, into a sum and difference, x negative 3, x positive 3. And from here then, we'll say each of these unequal to 0. And what two values can x not equal.
Negative, positive 3.
Right, negative 3 or positive 3. Here the positive 3, and then here the negative 3. So we'll say x cannot equal positive negative 3. Questions on this one? Do you see it's the same thing? Even when it's quadratic, you still set the denominator unequal to 0 because it can't be 0, and solve from there. And if it's quadratic, now you just do some factoring. Now number 19, this is kind of interesting. We got a 10x over an x squared positive 1. And so what we would need to do here, right, is to set it unequal to 0. So do that with me. We'll say x squared plus 1 cannot equal 0. And then we would need to factor. But what is this expression, anyone? A sum of squares. Can you factor a sum of squares? No. In fact, if we took what Noah was thinking a moment ago, imagine for a moment if we had just let Noah do what he wants to do. And he says that x squared equals 9. Well, remember, x means what, right? It's unknown. What squared would ever equal a 9 class? Well, 3 squared or negative 3, right? If we took that same line of thought here and moved the 1 over, we would get x squared equal, is unequal to negative 1. What, when you square it, would give you a negative? Nothing. Because when you square something, you always get positive. There are no real excluded values. They're called imaginary numbers. We'll talk about them next year. But for this, x can be whatever. There are no excluded values. You can put anything you want in for x on this one. So no excluded values is what you put here. Anytime you see a sum of squares denominator, because it cannot factor, you cannot get excluded values. So a sum of squares in the denominator does not give you excluded values. Do number 20 and 21 at your seats. 20 and 21 at your seats. All right, number 20. Let's go to Brecken. What did you get for your excluded value or values on number 20? Number 20, let's see, we got an x negative 3 is equal to x squared negative 1. So we need to take the x squared negative 1, set it not equal to 0, correct? Can this factor? What is it? Right, this is a difference of squares, and a difference of squares most certainly does factor, doesn't it? So we should have gotten actually two values that are excluded. X cannot be, right, negative 1 or positive. Well, we just combine that and say positive, negative 1. If you wanted to, you could say x cannot equal negative 1 or positive. You could write it that way as well. Either way is fine. I'm lazy. This is easier. How many got positive, negative 1 as your excluded values? What about number 21? Did you get that one, Brecken, for redemption? Good. How many got x cannot be negative 7 halves? Now look at 22. We haven't talked about cubic equations or cubic expressions. We got this x cubed negative 1. Again, I don't care anything about the numerator. Numerator can be whatever it wants to be. It's ugly. I don't care. I'm focused on the denominator. This is not quadratic. It's cubic. So for this, when I set it unequal to 0, let's do what Noah had suggested, that other problem, and just move the negative one over as a positive. To get x cubed cannot equal class 1. And now you have to ask yourself the question, what would you cube to equal a 1? 1, right? 1 times 1 times 1 would be 1. So therefore, x cannot be 1. Is there anything else you could cube to get a 1? Nope. The whole positive negative thing, that works when you square something, right? Negative 5 when you square it gives you 25, and positive 5 when you square it gives you 25. But if you cube a negative 1, what do you get? Negative 1, right? So only positive 1 is our singular excluded value on number 22. Questions on that one? Number 23. Solve that very quickly. 23. Find the excluded values on number 23. Maddie, what did you get for your 2 excluded values? 3 and negative 2. How many had those same excluded values on this problem? Number 24. What is the excluded value on 24, class?
Wait, what? Wait, no, hey, negative.
Well, you're looking for a value. What value can x not equal on number 24? Okay, what's the denominator?
X.
And the denominator is not allowed to be 0. So what can x not be? 0. That was almost insultingly easy, right? Gets you all used to factoring and stuff, and it's like, oh, it's just not equal to 0. Yeah, x can't be 0. Questions on 24. Any questions on excluded values? Any questions on that? We feel like we got a pretty good understanding of what we're talking about. All right, another thing we want to talk about with fractions, remembering that a fraction bar literally means what, class? Divide. I think I saw you mouth divide, or is that just a yawn? It looked like a yawn while you were trying to say something. Divide is correct. That's what a fraction bar means. So thinking of our division rules, if you divide unlike signs, class, you will always get a negative. But if you divide like signs, you'll always get a positive. Next section of your notes, signs in fractions. Signs in fractions. There are 3 important signs in a fraction. When you look at a fraction like, just give me a nice easy fraction, Brecken. 1/2. Thank you, sir. There's actually 3 signs in there that you don't see. First of all, that's a positive 1/2. You just don't normally write the positive. Not only that, but the 1 specifically, the numerator, is a positive 1. And the 2 is a positive 2. There are 3 signs. The sign of the entire fraction, the sign of the numerator, and the sign of the denominator. If they're positive, we cool. Just don't worry about it, right? The only issue arises if they're negative. So here are your rules. If one of these signs is negative, if one of these signs is negative, maybe instead of the 1 being a positive, the 1's a negative. Or maybe we've got a 2 over a negative 3. Or maybe we have a negative x over y squared, something like this. Do you see how in each of these, only one of the signs is negative? Here it's the sign of the numerator. I can leave these positives understood. Here it's the sign of the denominator. Here it's the sign of the fraction. What do you do if there's only a single negative? You make sure it's out front. Because when you divide a negative by a positive, it gives you a negative fraction. You divide a positive by a negative, it gives you a negative fraction. Here, the negative's already out front. We good. So if you only have one negative, make it the sign of the fraction. In other words, move it out front. If you only have one negative in a fraction, move it out front. Pretty easy? What if you have two negatives? Well, if you have two negatives, something like this. Well, here, the negative divided by positive would give you a negative, but you already have a negative out here, so it's as if they would cancel. Or here, positive divided by negative would give you negative, but you already have a negative out here. Here, negative by negative is a positive, so no matter where they are, if you have two negatives, cancel them. That's a horrible pen. If you have two negatives, cancel them. Just gone. 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 Make sense? One negative, what do you do, class? Move it out front. Make it the sign of the fraction is technical, but move it out front, okay? Two negatives, cancel them. What if all three are negative? So literally anything that can be negative is negative. Well, right here, negative divided by negative, class, positive. But we have a negative out front, so it stays negative. Basically, you're going to cancel any two of them. I can cancel these two. I can cancel these two, but now I only have one negative that has to move to the front anyway. So which two does it make sense to cancel? The numerator and denominator. So if there are three negatives, cancel the negatives in the numerator. And I'm going to abbreviate numerator N-U-M and denominator, that's D-E and O-M. If there are three negatives, just cancel the negatives that are in the numerator and denominator, because it's going to leave you with one negative, which you wanted out front anyway. So just cancel those two, so the one that you want out front is already out front, and we lazy. All right? So one negative, class? Move it out front. Two negatives. Three negatives. Cancel the numerator and denominator, so the only one left is already out front. Questions at all on this? All right, we're going to practice more with fractions tomorrow. For tonight, I'm going to give you more factoring practice to make sure we're good to go for what we're going to get into tomorrow. Your homework this evening is to do page 409, the review 1 through 14. Page 409, the review 1 through 14. Page 409, the review 1 through 14. Today is January the 6th. January 6th, it's Wednesday. All right, have a wonderful rest of your day. You are dismissed.